Hey everyone, welcome to another Explainer. Today, we are transforming complex Cambridge mathematics into a beautifully structured visual toolkit that you can actually remember. You know, if you've ever stared at a geometry problem and felt completely lost in a sea of angles and intersecting lines, you are definitely in the right place. We're going to break down the absolute fundamentals of the 0580 syllabus, specifically focusing on the rules of similarity and the unbreakable properties of circles. Let's get into it.
Here's a quick look at our agenda for today. We'll start with the power of similar shapes, move into scaling area and volume, cover some essential circle vocabulary, and finish up with the unbreakable circle laws.
All right, Section 1, the power of similar shapes. Let's see what this is all about.
So in everyday language, calling two things similar just means they kind of look alike, right? But in geometry, it has a very rigid, specific definition. Similarity is a strict mathematical relationship governed by a constant multiplier. We call this the scale factor, and it's usually represented by the letter K. If shape B is similar to shape A, it means shape B is basically a perfect photographic enlargement or reduction of shape A. Every single length has been multiplied by that exact same K, while, and this is absolutely vital to remember, every single inside angle remains completely unchanged.
It's really easy to get lost when you're just looking at a bunch of shapes on an exam paper. So let's pose a question about how we actually move from a known shape to an enlarged one. Imagine you're given two regular pentagons, P and Q. The problem tells you Q is an enlargement of P. So how do you find the key that unlocks the rest of the puzzle?
Well, this brilliantly illustrates our very first rule. Always find your linear scale factor first by comparing the 1D lengths. You simply take a known side length from the new shape, Q, and divide it by the exact matching side length on the original shape, P. That ratio right there gives you your K. And once you have K, you hold the master key to finding literally any other missing 1D length on that shape.
Moving right along to Section 2, Scaling Area and Volume.
Okay, I absolutely love this table because it is quite literally the ultimate cheat code for scaling questions. This is exactly where examiners love to set traps, and it's where most students drop crucial marks. But look closely. Notice how the exponent perfectly matches the dimension. If you're dealing with 1D lengths like a perimeter or a side, your multiplier is just K. But the second you move to a flat, 2D area, your multiplier becomes K squared. And for a 3D volume, you guessed it, K cubed. So think about what that actually means. If you increase the square's side length by a factor of K, the area doesn't just increase by K, it explodes by K squared. For example, think about an enlargement scale factor of 3. The new length is 3 times bigger, but the new area is 3 squared, meaning it's 9 times bigger. The volume would be 3 cubed, which is a massive 27 times bigger. It scales up incredibly fast.
Let's actually trace the mathematical proof for a cuboid just to show exactly why the volume factor is K cubed. Our base cuboid has a volume of length times width times height. When we enlarge it by our scale factor K, the new length is K times L, the new width is K times W, and the new height is K times H. When you multiply all those together to get the new volume, you are multiplying K 3 separate times. And that's exactly why you get K cubed times the original volume. To really put this into practice, think about this classic capacity problem straight from the source material. You have two similar 3D troughs. Let's say you've already figured out the linear scale factor between their heights. You know the small one holds 10 liters, so how do you find the capacity of the large one?
Here's the secret. You cannot just multiply the 10 liters by the linear scale factor. You absolutely must use the volume factor, which is the scale factor cubed. This is probably the #1 mistake students make. Capacity is volume. Therefore, you must cube your K before you multiply it by the 10 liters. Always remember the dimension rule. By the way, if you are finding these strategies helpful, make sure to subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Let's keep going.
All right, on to Section 3, Essential Circle Vocabulary.
Now we are pivoting to the elegant, heavily rule-bound world of circles. But before we learn the laws, we really have to speak the language. Take a second to lock these fundamental terms into your memory. The circumference is just your perimeter. An arc is simply a piece of that perimeter. A chord is a straight line drawn from one edge to another, and the space it traps is called a segment. A sector, on the other hand, comes all the way from the center, kind of like a slice of pizza.
And I want you to pay special attention to the tangent, because this unique line is the hero of one of our most important theorems coming up.
Imagine a bicycle wheel resting on the flat ground. That ground is a tangent. It perfectly grazes the edge of the circle at exactly one single microscopic coordinate. And it never ever goes inside the circle itself. Which brings us to Section 4, the unbreakable circle laws.
Now for the grand finale. When you look at a complex circle problem on an exam paper, your brain should immediately start scanning for specific visual blueprints. And this number, 90 degrees, is going to be your absolute best friend. In the chaotic web of lines inside a circle geometry question, finding a hidden 90-degree right angle is almost always the key to unraveling the entire problem. So, whenever you see a triangle built on a diameter that reaches out to the edge of the circle, you instantly know you have a right angle. This is Law 1, the angle in a semicircle. Honestly, it doesn't even matter where point C is on the curve. As long as the triangle's base is the dead center diameter, that peak angle hitting the circumference will be a perfect 90 degrees, every single time.
Similarly, when a tangent meets a radius, it acts like a perfect perpendicular wall, instantly creating a right-angled intersection. We call this Law 2. If you draw a straight line from the center of the circle, which is the radius, out to the exact point where a tangent touches the outside edge, the angle they make is always 90 degrees.
The math backing this up is actually really beautiful. It relies on congruent triangles sharing a common radius to prove that perfect 90-degree angle. And remember, congruent just means they are the exact same shape and size. Because the radii are equal and the triangles share a common side, those intersection angles are basically forced by geometry to be identical 90-degree right angles. Now, what's really fascinating here is how we can prove our third law by simply slicing the circle up into isosceles triangles. We already know the radii of a circle are all equal length. By drawing lines from the center out to the angles, we create triangles with two equal sides. But using the basic rules that a triangle's interior angles add up to 180 and angles around a center point add up to 360, we arrive at a truly brilliant algebraic shortcut.
This leads us to Law 3. It means if an angle on the edge is 45 degrees, the angle at the center resting on that exact same arc will be exactly 90 degrees. Think of it like a slingshot pulled back from an arc. If you pull it to the center, the angle is pretty wide. But if you pull it all the way back to the opposite edge of the circle, the angle becomes exactly half as wide.
And this concept brings us perfectly to our fourth and final law, which is actually just a direct spin-off of the previous theorem. Angles in the same segment of a circle are equal. When you draw multiple angles from the exact same starting points on an arc, they are permanently bonded together by this rule.
Think about it logically for a second. If the center is always double the edge, then every single edge angle sharing that specific arc must be identical to one another. If the center is 100 degrees, then every single point you hit on the opposite circumference coming from that arc has to be exactly 50 degrees. There's no way around it. They are locked in.
We've mapped out the tools and the proofs today, so the next time you face a tough geometry puzzle, which of these visual blueprints will you rely on first? Remember, do not let the complex diagrams overwhelm you. Look for the 1D scale factors, hunt for those hidden 90-degree angles, and always trace your arcs back to the center. You have the master toolkit now. The real question is, when you turn the page to your next impossible-looking exam question, which hidden shape will you unlock first? Thank you so much for joining me on this explainer. And remember, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Keep practicing, and I'll see you next time.